Thank you, everybody, for attending today. My name is Jeremy Douglas, Hohmann and Barnard. I am the Technical Services Director here. I've been in this industry for probably going on 15 years or so now. I've worked with various types of wall systems. I've worked certainly with full bed masonry walls, as we're going to talk about today, as well as plenty of other types of walls. But today we're gonna focus on full bed masonry, and we're going to talk a lot about a lot of these different systems. You know, it used to be that I would give a seminar specifically on anchorage systems or specifically on flashing and drainage systems. I've got 2 or 3 seminars that I give now on air barriers and those types of systems, but it's really hard to talk about any one of those where you don't talk about the others, because all of these systems really need to come together to form a masonry wall system, and the wall system should be looked at in just that way, as a system, as a synergy, because again, they're also dependent on one another. We need to understand what masonry's vulnerability is, and everybody that's here and tuned in today certainly knows what we love about masonry. Its aesthetic look and its strength and longevity, but really we need to understand how vulnerable masonry can become to things like thermal expansion and moisture penetration. And we're going to talk a little bit about both of those issues today. I've got a lot of ground to cover here, so if it sounds like I'm speaking quickly, it's there's a reason for that. There's just so much to cover, and in fact, we're only going to touch on a little bit of all of these things. So without further ado, I suppose we should jump right in. So what I really can't stress enough is that you look at the masonry wall today as it is, and understand what's going on in that masonry wall. So you're going to have a backup wall, whether that's a CMU backup or a stud and jip backup, and that backup wall is going to have some type of a weather barrier on it, be it an air barrier, vapor barrier, what have you. You're going to have a cavity wall, insulation, flashings, all the stuff going on. Then you're going to have your veneer wall, which today needs to have weeps at the bottom of that cavity. Also needs those same vents at the top of the wall section. And there's a reason that we do this. This is so that we're equalizing the pressure of the interior cavity to the exterior air. And in reality, what we want to do is sort of, keep that pressure as equalized as we can, because any air that's moving within that cavity wall is going to have a tendency to carry moisture with it. And if we have any breaches in our building envelope, that's where that air is going to go. So we really want to limit the amount of air pressure as much as we can control through the use of those vents. The purpose of showing this is that you really need to understand that a masonry wall is very little more than a rain screen, okay? And that means that this wall is meant to be wet. It's going to get wet. We're not going to prevent it from becoming wet, whether we're talking about thermal bridging issues or we're talking about cracks that form later on, or just the fact that the mortar joints, even if we use an integral water repellent in the mortar, that eventually is going to deplete, and we're going to have some absorption of moisture in through mortar joints, which also account for 20% of that wall face. So no matter what we do in the course of installation, this wall is going to get wet. But the good news is it's designed to be wet. With things like flashings and drainage planes, we sort of help to alleviate that. But you, in the course of installation, need to understand that this wall is going to be a wet wall, and again, it's meant to be and designed to be. As I said earlier, we have issues with our concerns, I should say, with expansion and movement, thermal expansion within the wall, as well as moisture penetration. And we're going to talk a little bit about both of those things here today. Thermal expansion stresses are they're dealt with and remedied through the use of that horizontal wall reinforcing. This is the wire that sits in your bed joints This is accomplished either with the truss type reinforcing or ladder type reinforcing. Now, what you need to know about the code, ACI 530 code, which we revert to, and I'll be referencing here quite a bit, either ACI 530 or TMS 402. There's a joint code console. Both of these types of reinforcing are acceptable to utilize to that code. The truss reinforcing gives you 20% more steel. However, if you've worked with that and you have any type of horizontal reinforcing that's going to go into the cells of those block, rebar, grouting, things like that, sort of difficult to work around those cross wires on the truss, which is why we tend to use ladder reinforcing. And I recommend that designers that they're specifying ladder reinforcing because it makes your job a whole lot easier. The one thing that you need to know about the difference between the two of these, and again, looking at that code says that the steel that you have in those bed joints can be no more than half the thickness of the joint itself. So when we're working with 3/8 inch mortar joints, you're limited to 3/16 of an inch steel in the joint. Well, here's the problem. If I told you to overlap the truss reinforcing and you just simply set one piece on top of another piece in the bed joint and continued on, that would be beyond the parameters of that 3/16 of an inch of steel that the code allows. So really to install the truss reinforcing correctly, you would have to take a pair of bolt cutters and cut and snip so that you could actually nest those two wires together. With ladder reinforcing, it's already manufactured that way for you, so it's much, much easier. Again, I tell these designers all the time, if something's easy to install, it tends to get installed correctly. And again, that's why I usually recommend the ladder reinforcing. If the designers tend to like, if the architect you're working with tends to like the truss reinforcing because it has more steel in it, you can maybe make a recommendation that he goes to a heavier steel. So typically in the industry, the standard has always been 9-gauge steel all the way around. But you could make that compromise and say, okay, well, if we can use a ladder type reinforcing, it's going to be easier for me to install on the job rather than the truss reinforcing. Maybe we go from 9-gauge to 3/16 of an inch, and that will tend to appease the designers. So just something else for you to think about. Finishes on these. So the same code says that any exterior wall or an interior wall that's going to have a high humidity, that humidity being 70% or greater 50% of the time, requires that your finish of the material be at a minimum hot dip galvanized, and if not, stainless steel. What this means to you is that you cannot use a mill galvanized wire on an exterior wall. It doesn't meet the requirements of the ACI 530 TMS 402 code. So anything that's on an exterior wall must be hot dip galvanized, or of course stainless steel. Something you should know too about stainless steel, you really want to make sure that any stainless steel that you're purchasing and working with in a wall, and this is whether it's specified that way or not, really should be at a minimum 304 stainless. Okay, and I bring this up because there's a lot of 301 stainless that's out there, and here's what I want you to know about 301 stainless and what that really means. When your neighbor goes to Home Depot and he buys a grill, and a year later, after it's been sitting out in the elements, that stainless steel in the grill starts to rust, and everybody's curious how that happens because stainless steel doesn't rust, right? Doesn't rust, doesn't pit. Well, it does, and that's from a lower quality stainless steel. So if you're utilizing a 301 or a lesser quality stainless steel, and we're putting it in a masonry wall environment where we've got a lot of things happening, we've got tremendous fluctuations in humidity and temperature, and you've got mortar coming into contact with the metals, and sometimes we have some other metals in the walls. The 304 stainless is likely going to cause you problems later on down the road. So just if we're buying the right grade materials to begin with, maybe we don't have those issues. So anyway, that's just a side note. So with regard to wall reinforcing, and I mentioned before, you know, that truss type reinforcing can be a little bit difficult to work with when we've got vertical reinforcing rebar, grouting cells, things like that happening. And here's a great example of that, where the you know, the rebar more or less pushed the wire outside the wall. Obviously, this is a little bit extreme and really should have been remedied well before air barrier was put on the wall. But here's what you really need to know about the installation of wall reinforcing, what pertains to this picture and what pertains to the code. That code also says, that's again that TMS 402 ACI 530, says that any wall reinforcing or any ties or seismic wire, things like that, any of the stuff that's being installed in a joint needs to be at a minimum 5/8 of an inch interior of the wall from the face of the joint. Okay, so obviously this being installed on the outside of the wall, not acceptable, but more importantly, when we are installing this stuff needs to be at least 5/8 of an inch inside that wall. And part of the reason for that is so that, you know, not so much with a block wall, but with a brick wall, if we've got seismic wire in there, it needs to be 5/8 of an inch in, because later on, if we're going to repoint and grind in, you want to make sure that you're not hitting that wire. So, as many of you know, we can also integrate the anchoring of the brick to that CMU backup. This, of course, was accomplished for years just by taking a rectangular wire tie and welding it to the wall reinforcing, and then it would come straight across and into the brick by about halfway. The problem with that, of course, as you well know, is that really you had no adjustability. So then later on, the system that we're all familiar with today, the hook and eye system, or the pintles and eye system, was developed, and that's where that set of eyelets, as you see on the left-hand side, that set of eyelets was welded directly to that wall reinforcing, and then you had a set of hooks that you could incorporate with the eyelets, and that would afford you some adjustability up and down. That same code, ACI 530, TMS 402, allows for 1 1/4 inch of adjustability up and down when we're utilizing 3/16 inch wire on an open system like this. And open meaning that pintle, that set of hooks, can be engaged and disengaged. Now, 1 1/4 inch is probably fine if you're working with standard size brick, modular brick. When you start getting into the larger bricks, utilities and jumbos, 1 1/4 inch doesn't mean a whole heck of a lot. In the 90s, I believe it was 90s, the closed system that you see on the right-hand side, the set of loops, was developed. And because that system is closed, it actually allows for an extra inch of adjustability. But there's also some other characteristics of that system that I'll share with you in just a moment. But I want to talk for a minute more about these pintles. Again, the code only allows for 1 1/4 inch of adjustability with those, and of course we looked at it and said, well, how can we get more adjustability for these guys with this system that's everybody's familiar with? And the answer was to go to heavier gauge wire. But then, because of the way the code's written, if you go to a heavier gauge wire, then essentially you'd have to go to a heavier mortar joint. But what we were able to do is take the back side of that pintle and flatten it out. So you take a 1/4 inch wire, and then in order to get a 1/4 inch wire into a 3/8 inch mortar joint, you've got to flatten it down to 3/16 of an inch. And that's what was accomplished here. And that's that now allows you almost 2.5 inches of adjustability utilizing that same open pintle system. And then you may also have seen changes recently on the standard types of pintles and changing the profile here, so that now you see at the radius where the stresses are put on that anchor, essentially by flattening that out, it creates a beam and makes it much, much stronger. I'll give you an example of what stronger here means. This ACI code says that when you test these pintles, or you test these anchor systems out, when you put a 100-pound load on them, either in tension or compression, meaning that you're pushing against the wall or you're pulling the wall away from the backup, you can have no more than 0.05 inches of deflection. And typically speaking, your standard type pintle, like you see here at the top of the screen, you would net 130 or 140 pounds or so before you would make that 0.05 inches. Here, with the compressed leg, and this will show you an example of the test, what that looks like. And this is an 1.5-inch air cavity with a 4.5-inch wall. So we're at 6-inch span here, and you're over 800 pounds before you're meeting that 0.05 inches of deflection. So the code's 100, and we're showing 800 here. And that's something that I think as an industry we need to be moving towards. So we don't just do this because it's fun to do, or it's fun to screw everybody up with new materials out in the marketplace, but we do it because really there's a real need for it. If you look at what's going on with the weather, and you look at things like wind loads and how much they've changed even in the last 10 years, this ACI 530 code that everybody sort of works around in the world of masonry was written something like, well, it was written almost 30 years ago, and it was written utilizing data that they had from 50 years prior to that. So, is a 100-pound load really good enough for today's standards for the buildings that we're building for the next 50 or 100 years? I don't know. I don't tend to think so. I think that that's something that really should be looked at. Again, looking at the data that we have with regard to wind loads, and certainly the coastal cities have seen more Category 4 and 5 hurricanes in the last 10 or 15 years than they had in any years prior, and they see them maintain Category 4 and 5 status when they hit. I'll give you this example, and certainly we've all heard about tornadoes hitting, and they hit in metropolitan areas now. It's not just in Kansas and Nebraska anymore. It's these hit in downtown areas like Atlanta and Queens and Springfield, Massachusetts. In New York State, it's funny. We saw a tornado here in New York maybe once every 20 or 25 years. I had 5 touchdowns last week, and it's just unheard of. So, things are definitely changing, and I guess that's why we make these changes as well. But to that, what you need to be aware of is that when you see these types of hooks out in the market, or you see these, on a job, they're made to work with a certain size eyelet, and that means that the standard type pintles, the old style pintles, don't work with those new eyes, because the code also says that you are allowed no more than a 1/16 of an inch of play and movement laterally inside when those hooks are engaged. So they can't shuffle around. And if you take the older non-compressed version of those hooks and put them into an eyelet meant for the compressed version, they're gonna move all around. So you need to be aware of that and know that if you take a tie and engage it to an anchor, and there's a lot of movement, a lot of play in the direction that the wall is going to move, that something's probably not right there. One of the reasons that we really like this system, if you're somebody that's seen these before or worked with these before, is because when a masonry wall is built, okay, a brick comes out of a kiln, it's as small as it's ever going to be. And that means that your wall is going to be in a perpetual state of motion or growth. But they move in all directions, right? So they move vertically as well as laterally. And with a hook and pintle system, it only allows for that growth to take place vertically, whereas this type of a system allows for both vertical and lateral growth, which basically means that you're going to have a lot less cracking in that wall as time moves on. But that's what this particular system was developed for, and this is utilized mostly in New York City and surrounding areas, some. But anyway, that's the idea behind that system. So one other thing that you really need to know about the ACI code, okay, is that it says that any type of wire or you know, anchorage, any of the stuff can't be bent on site. And so here's an example of somebody coming in and applying an air barrier, and when he wanted to go and install that transition membrane between the CMU backup and the overhead relieving angle to make that easier for himself, he just sort of bent all of those out of the way. Code says no. And, well, actually, no, what the code says is that anything that gets bent needs to be replaced at the discretion of the architect. Well, what do you think is going to happen? Architect is going to require that you remove and replace something like this. So just know that, be careful with either these loops or even the eyelets. You know, if you've got 2.5 inches of insulation, those eyelets stick out of that CMU backup wall quite a ways, and you know, very easy to knock into them or bend them out of place. And again, anytime that steel gets bent, it gets weakened, and it's up to the architect as to whether or not you can leave it in the wall, which we all know what the scenario there is going to be. So, speaking of air barriers, we'll move our discussion toward that. I'm not going to go into a lot of air barrier science here. It's a lot of stuff that you don't need to know. What you need to understand, though, with regard to air barriers is sort of how moisture will pass through your building envelope. And it's going to occur one of two ways. It's either going to occur through diffusion or through air movement. Okay, diffusion is where water vapor as a gas passes through material. And this happens through everything. Okay, you can diffuse vapor through plywood sheathing. You can diffuse vapor through paint. You diffuse vapor through an air barrier. What's different is air movement, what we refer to as channel flow, which is where air actually carries moisture with it. So it picks it up, carries it, and more or less drops it off. I'll give you an example of the test that that took place in Canada and sort of you know, sprouted all of this air barrier technology. And what they did is they chambered. In 2 different chambers, they chambered 2 pieces of gypboard. Chamber A had a piece of gypboard that was completely continuous. Chamber B had a piece of gypboard that had a 1-inch by 1-inch hole cut through it. And basically what they did is they circulated air on the front side and collected moisture on the back side over a 30-day period. The completely continuous piece of gypboard netted something like 7/10 of a pint of moisture after 30 days. The 1-inch by 1-inch hole, that piece of gypboard, circulated something like 63 pints of moisture after the 30-day period. So when we talk about diffusion or we talk about air movement is a much, much, much bigger deal. Okay, the ABAA, Air Barrier Association of America, will tell you that a hole in your air barrier the size of a quarter will move as much as 25 gallons of water per month. That's a lot of movement. That, of course, again, depends on what the air pressure is inside that cavity wall. And as I said before, that's why we're putting those weeps and vents in that veneer wall closer together, because the more vents, the more size that we have in our vents, and the closer together that we're putting them in that wall, then the more likely we're going to, or the better that we're going to equalize that pressure. But think of a wall that has, say, no vents at the top, and maybe at the bottom we're using those little tiny, you know, those 3/8-inch round plastic weep holes. Maybe those weep holes are stuffed with a wick in the back side of them. How much air are we really moving into that wall? A wall like that, when you start putting stack pressures and other types of pressure on the wall, again, I'm not going to go into all the air barrier science. I'm not going to do that to you this morning. But you start putting all that type of pressure onto a wall, mechanical pressure and whatnot, and you can actually reach pressures inside that wall up to 35 or 40 psi. And that's moving an awful lot of air and taking an awful lot of moisture with it. So again, you need to realize that We want to stop the movement of air in the cavity, and that's sort of what the purpose of all of this stuff is. So air barriers stop air leakage. Vapor barriers basically slow down diffusion of materials. And what you need to know there is that all air barriers are not vapor barriers. All they do, what they're meant to do, is to stop the movement of air. You've got a lot of different materials that are available to you out in the marketplace. There are certainly still sheet materials. I remember when air barriers first came to the Northeast, and we were wrapping, 18, 20-story buildings in 36-inch asphalt type flashings. The technology has certainly improved quite a bit since then. The big thing about air barriers, though, air barriers or vapor barriers, either one, is that they really, really need to be continuous. And again, that goes back to what I just said a minute ago about having that quarter-sized hole moving 25 gallons of water. Well, that shows just a lack of continuity, right? So continuity is absolutely key. And you've got to consider that when you're looking at the material that you're using. Now, obviously, you're going to use whatever specified on the project, certainly. But you've got to know requirements from manufacturer to manufacturer. An example, there are some sheet membranes out there that do require primers be installed prior, and there are some that don't. There are some sheet materials out there that with a primer may stick to a CMU backup wall. Likely, I'd be suspect of a sheet membrane on a CMU backup, just because no two CMU units are really, from manufacturer to manufacturer, are really the same, right? Some CMU has a lot more voids and a lot larger pores in it than others do. Of course, CMU also is continually dirty and dusty, so probably much more likely candidate for a fluid-applied air barrier, liquid-applied material, which is probably a lot easier to gain continuity on as well. But you also want to make sure that you know what manufacturers are requiring for fluid-applied barriers, because there are some out there that will say, okay, well, as long as you've got this material on, between, say, 20 and 27 mils, you're going to have the permeability rating that your designer is looking for. Well, 20 to 27 mils is doable in the field. There are also manufacturers out there who will tell you, well, no, this material needs to be on somewhere between 8 and 12 mils. And if you're the guy who's applying that, or if you have a laborer who's applying that, more importantly, really, really difficult to control that type of thickness. 8 to 12 mils through a paint sprayer, very, very difficult, which obviously makes, in some cases, the sheet more promising. So again, this is all just predicated on the notion that you're even installing the air barrier, which I tend to recommend. And I know I was talking with some of the guys at IMI last week as well, and I know that they're doing a lot more with air barrier programs and things of that nature, because in reality, if there's a leak in that air barrier, or there's a leak in the wall, who's going to get the call anyway, right? The wall contractor is going to get the phone call for that, so why not take control over that part of the system? The big deal with air barriers, and again, you can have 75,000 square feet of sprayable fluid applied barrier, and likely you and your laborers are going to have absolutely no problem maintaining continuity there. Where it gets to be difficult is the transitioning. Okay, so we're not just talking in transitions about openings and penetrations, but also where dissimilar materials meet, which can be really, really tricky. So as an example, if you've got a building that's comprised of structural steel and then CMU comes up and meets that steel, well, that steel column can be as much as 3 inches inside the face of the CMU, and of course, you're going to have a gap to span of about 14 inches. So things like that get to be fairly tricky, and certainly expansion joints need to be dealt with properly. But the whole idea behind a building envelope or air barrier is that basically we're wrapping the whole thing sort of like a present, and you're isolating those openings, and that's the key there. it's actually fairly simple, especially if you're working at all with flashings and you've installed, outside corners and you've cut those and that type of workmanship is the same workmanship that we're looking for here with air barriers. Really no different. Just that attention to detail, those window details and things of that nature. The other thing that really you need to look at with regard to air barriers is how they're being met with the roofing material and how they're, because again, if you're the one that's installing those air barriers, that's going to be a critical connection for you to make, both with the roofing material as well as whatever's happening below grade or happening at the slab. And again, those details should be spelled out for you, but you need to understand that they are critical connections, because typically they're not going to be the same system. They're going to be a different manufacturer, different system, and those two things need to be compatible at those interfaces. So here's something, and I see this an awful lot. Okay, and I don't pick on Tyvek by any means. They've certainly been around a long time, but I will pick at the installation of the stuff, or how the stuff winds up getting installed a lot of the times, because, and I see this, thousands and thousands of rolls of Tyvek being used as commercial air barrier. But what I haven't seen is a single roll of Tyvek tape. And if you're installing this stuff at all, you've got to realize that this also needs to be continuous to work. When that's being installed, how's it going up on the wall? Typically a tack hammer. Every time that you're hitting that with a staple, you're penetrating it. And the same thing goes for the anchorage. When we penetrate that with an anchor, now we've penetrated the air barrier again. So, can it be used? Well, sure, but a lot of these, basically the manufacturer's instructions need to be followed, and I guess that's where I'm coming from, is that typically when I see this stuff installed on projects all over the place, those instructions aren't being followed so much. It's basically just being overlapped, stapled, and called good. And it's really important that we're paying attention to details, especially like this. Going back to what I said before, a hole the size of a quarter is going to move 25 gallons of water every month. And whatever anchoring system that we're looking at needs to protect the integrity of that air barrier. That's absolutely key. And now, as we're moving into discussions about steel stud construction, we're going to talk about that, because with steel stud, whether you're installing the air barrier or not, you're guaranteed to penetrate it now. So it means that you've got a little bit of responsibility with regard to how that's done. Can it be done? Absolutely, it can be done, and it's done all the time. Again, as long as it's detailed properly, and we'll talk about how we do that. Before we get into the air barrier subject, though, I want to talk to you briefly about anchorage for steel studs, because some things here have certainly changed. Now, we move the insulation from the inside of the studs to the outside of that wall, and we do that to move the dew point out, which is more air barrier science stuff that I promised you I wasn't gonna hurt you with this morning. But the anchors that we use need to go through the insulation, number one. And I can't tell you how many times I still see a regular flat-backed, type of an anchor without those prongs, basically just at the surface of the insulation with fasteners that go through back to the stud. The fasteners alone shouldn't be depended on to make that connection. It's that anchor needs to go all the way through the insulation, and it also should go through the sheathing and go make direct contact all the way back to that steel stud. Okay, so you want to make sure that basically your anchorage is going through everything. Your anchor is connecting directly to the stud. It's touching the stud and making its contact point there. Certainly, we've all worked with this type of an anchor, and this will certainly do that for you. This goes all the way through the insulation, goes through that sheathing, makes a good seal. But as I said before, now we're penetrating an air barrier, right? And isn't that of concern, because this is going to penetrate it. Let's see, there's 1, 2, 3, 4 points on the prongs plus 2 more fasteners. That seems like an awful lot of anchor coming through that air barrier. And how do we deal with that? Well, it's actually very, very simple. And this is sort of what the detail is going to look like. But 2 things going on here. Number 1, the air barrier that you're sealing up against, the air barrier that you're utilizing, it's really helpful to you if that air barrier is any type of self-healing, okay, self-sealing type air barrier. That means that it's going to have some viscosity to it. It's going to have some stretch and elasticity. And it's probably going to be applied at a minimum of, say, like 18 mils. That's going to be key. Anything less than that is really going to be too thin to really give you any kind of a gasketing property. But that should be number 1 consideration, is that air barrier going to be self-healing material? And then number 2, as we've done over the years in other scenarios anyway, just take a piece of self-adhering tape, okay, and slide that or install that over the top of the air barrier at the stud. This way now, when your anchor penetrates through the tape, it'll form a gasket there at the tape, but also it'll have the adhesive on the tape and the elasticity of the air barrier to help form a gasket. And we've done significant testing on this with regards to airflow, moisture penetration, and this is the key to this detail in keeping any of that out from the wall, and more importantly, keeping your air barrier continuous. And the same can be done, and in this case, when you're penetrating the insulation, because you're also charged with keeping the insulation continuous when you install that, right? So you can take that tape and put it at the face of the insulation as well, so that now your anchor goes through the tape seals at the insulation, it goes through the tape at the air barrier, seals at the air barrier, and now you've kept both of those systems continuous. If you follow this detail, you shouldn't ever have a problem with airflow or channel flow carrying moisture, as we mentioned before. With steel stud anchorage, you also have this anchor as an option. This is an anchor that goes on before the insulation goes up. So that's sort of nice because you can see right where your studs are, right? So you can again, air barrier, put your tape up at the stud, and then shoot this anchor into your wall and the stud. What I will say about this, guys, and I see this a lot when I see this type of anchor being utilized out in the field, this was engineered for 2 fasteners, and often enough I see folks only utilizing 1. You really should be using 2 fasteners with this type of an anchor. But these anchors are very, very strong, and in fact we utilize these as high-strength anchors, as you see here, utilizing that larger pintle that I showed you earlier in the presentation. Or we've got an anchor like this. And what we really like about this, with regard to your installation, is that you've only got 1 fastener every 16 inches here. So this is a huge labor saver. This anchor, the barrel type anchor, the one that you see here utilizes a pintle rather than that threaded, that other anchor that you have to sort of thread through the back side of it. But this has a gasket at the barrel. It's a fixed gasket, and that seals to the air barrier at the sheathing, which we like. And then the rest of the barrel is manufactured to the size of insulation that you're utilizing. This also has, and this shows it, but not very well. There's actually a gasket at this wing nut as well, a larger gasket that will help seal your insulation. So it helps to keep that continuous as well. And then you're utilizing a pintle, so basically you can have somebody go and zip all these in, and then basically you're just dropping a pintle in there as you're coming around with the brick. So it makes for a very, very fast installation. And then we like this because certainly it affords a thermal break with that anchor, which of course is what designers typically complain about with steel stud construction. Is, you know, they have a thermal bridge that occurs from the the exterior wall to the interior wall. So this sort of breaks that bridge. A lot more on that subject to come from us, just so you're all aware. When I talk about tape, what I don't like to see is this, and you shouldn't either. And I'll tell you why. Number one, I don't like to see it because this means that every 16 inches in either direction, you have 4 corners that may curl up and break away from the surface of the insulation. That means that basically if it comes off, now you've got a means by which air infiltration can occur. You know, here these guys did such a nice job taping up those seams and those corner joints, but likely they're going to have a problem. At least a few of these anchors are going to pull away from the face of the insulation. The other reason that you don't want to do this is because the roll of tape that I'm suggesting that you utilize is incredibly inexpensive to begin with. To do this means that you've got to have a guy sit there and cut off 8-inch pieces, stick 8-inch pieces up individually at the studs, but also take that release paper off of each and every one of them. And that becomes extremely time-consuming, and you're definitely not saving any money there. So full strip from top of the wall to the bottom of the wall, and then anchor into that. If you've got a full strip there, a lot less likely that you're going to have all of that material pull away. It's going to be continuous and going to be a lot more adhesive to the wall. So moving from anchorage and stresses and all that, we're going to talk a little bit about moisture issues. I'll tell you, I've seen moisture problems in a masonry wall just from a bad cleaning job. And if if a brick wall gets over cleaned, where we can run our finger across the bed joint, all the sand falls out, it means that those joints have become a lot more absorptive than they were meant to. And again, remember that your joints are 20% of your wall face. Certainly all the concerns about weeps and flashings occur, and those are a really big deal. Make sure we keep the weeps clear and making sure that the corner and end dam details and flashings are correct. Here's a little something, a little piece of advice that I pass on to you, whether it's in the specification or not. You are really going to do yourself a lot of favors if you keep materials out of the elements, out of the snow, out of the rain. Keep them covered, whether that means that you're covering them in the yard or they're under cover. Keep them covered, and also keep your walls covered. At the end of the day, make sure you're throwing a tarp or something over the top of the wall. You know, if it's Thursday night and you're leaving the job and you wake up Friday morning and it's just pouring rain, and it's going to pour Friday and Saturday, and maybe it rains, you get a thunderstorm later on Sunday. It's a lot of moisture that's introduced to that wall, and if that happens over the course of a month or two, you're introducing a lot of moisture in that wall that when we cap that wall over and the sun comes out, that moisture is going to come out of that wall. It's going to bring a lot of nastiness with it. Now, efflorescence, not that big of a deal. We can deal with that. But when we start looking at things like calcium that comes out of the wall along with moisture, becomes a lot more difficult to remove, and something that we don't have to deal with if we're not introducing a lot of extra moisture into the wall. So again, just a quick and easy benefit for you guys. Know certainly what you're dealing with as far as cracks and imperfections go in brick. Some brick are a lot more porous than others, and if you can remind a designer of that, it may be helpful to you in the long run to say, hey, the stuff has got a lot of openings in it. It's gonna take on moisture. Again, you're gonna install whatever's being instructed to install, but at the same time, it's just information that's helpful for everybody to know. And your mortar details are a big deal. So when you're laying block, make sure that your head joints are that full thickness of that face shell. Even if this is just a backup wall, that block is going to settle. When it does, where's that crack going to occur? If there's an air barrier over the top of that, is that a big deal? Well, yeah. Again, 1/4-inch size hole going to move 25 gallons of water a month. It all winds up inside there. We're going to be in trouble. So that's really, really important. Also, with joint finishes, You know, I don't recommend anything other than concave and V-shaped joints. What we want is we want a joint surface that's going to shed moisture away from the wall. And you know, especially where I'm from upstate New York in the Northeast. We start looking at, you know, these other types of joints, especially, you know, struck joints and flush joints. They're just not appropriate for the climates that we have here. Maybe down south they're a little bit better, but with freeze-thaw cycles and things like that, I don't want to trap any moisture in the mortar joints any more than I have to. So again, this is stuff that you have very little control over, but at least if you need to, you can make suggestions. Flashings, we'll talk about flashings here briefly. There's been some changes here with some details and some materials. Here's what you need to be cognizant of, and again, sure, you're going to use whatever's being specified, but there's a lot of stuff being specified that's not right. And you know, here's an example of that. The big thing now is looking at material adjacencies. So with air barriers that are there today being polymer based, okay, they require that we're utilizing silicones and urethanes to seal those or seal materials to those. When we're looking at flashings, okay, if we've got, say, an asphalt laminated copper flashing going up against a polymer based air barrier, well, those silicones and urethanes aren't going to stick to the asphalt coated flashing. By the same token, those asphalt-coated flashings require, you know, solvent-based primers, or sorry, not primers, solvent-based mastics, and those are, you know, possibly going to damage that polymer-based air barrier. So we really need to look at a lot of this kind of stuff here and say, you know, hey, you know, should we be using this material with this air barrier? You know, is this flashing really appropriate for what we're trying to do? And of course, what's your concern with flashing? You know, number one, how easy is it to work with, but also what's the exposure and things like that we need to be looking at. So again, we'll talk about some of these briefly here as we wrap up. Synthetic flashing, flexible metal flashing, preformed metal flashings. You know, PVC, and there's still plenty of PVC that gets used out there as flashings. One thing that I want you to really understand, there's not a manufacturer that recommends this as a flashing material. They all sell it, but it's never being recommended as flashing. So, you know, we all know it's inexpensive, and that's why it gets used. But really, if we can avoid using it, we probably should be. Rubberized asphalts. These type of peel and stick flashings, you need to know what these are being comprised of and why they do sort of what they do. These are 8 mils of extruded polyethylene film and 32 mils of that rubberized asphalt. That is the makeup of this type of a flashing. Again, looking at the masonry cavity environment with extreme fluctuations in temperature and humidity, if you know anything about polyethylene, it's very difficult to get things to stick to it and to stay stuck to it. And in the case of the fluctuations for, you know, like I said, humidity and temperature, becomes an environment where delamination is really, really easy to come by. Certainly, we like the peel and stick flashings because they're easy to work with, right? They're easy to form corners and end dams, wraparound columns, things like that. But the other thing we got to look at is the fact that, you know, they do puncture. And here's the big deal. I don't think that anybody's ever worked with an asphalt type of flashing that hasn't seen this kind of thing occur, or this kind of a thing occur, where that delamination takes place and the stuff actually melts. You know, masonry walls can reach temperatures 170, 180 degrees if they're exposed to the sun in the summertime, and some of this asphalt tends to melt at like 155, 165 degrees. So, you know, it's already sort of compromised with where it's going. So what I say is, if you've got to use a peel and stick flashing, look for a heavier polyethylene. Look for a polyethylene that's going to be woven, so it's going to give you a lot more strength, and a heavier polyethylene. So you go from 8 mils to, say, 20 mils. But also, your adhesive should be non-asphaltic. It should be like a butyl-based with a higher temperature melt. You know, it's going to stick every bit as well as what you're expecting it to, and you're not going to pay any more for it. So if you can, you know, seek that type of material out. Here's the one big change here with regard to the flexible metal flashing. We're all familiar with copper. and how that's been used as a flashing. I argued for a long time that there had to be a better solution than copper, because the problem with copper isn't necessarily the cost, is it? It's more the fluctuation of the cost. So if you call looking for 15,000 square feet of copper, or price on 15,000 square feet of copper in February, and then you're actually awarded the job and get to place your order for the material in, say, June or July, that price can move as much as 40 or 45%. And that's where everybody gets frustrated, right? Because it's rare that it ever moves the way in favor. What I looked at was stainless steel, and you know, stainless steel in a thin foil form doesn't really fluctuate that much. In fact, what I'm looking at hasn't fluctuated much more than 5% in the last 3 years. Big difference from copper. And everything in the wall is already stainless steel now. So like our termination bars and drip edges and things like that are stainless steel. But you're also getting higher strength, higher puncture resistance, higher tensile strength. And typically, your stainless steel is going to come in less expensive than a copper flashing is. So this is something to look out for as well. And again, what I've been testing out is a 3-ounce material. Super strong, holds a crease, really, really flexible. And again, a lot less expensive, which, again, helpful to you. All in all, I really think that we should be looking at asphalt-free flashings. They're just a lot cleaner, a lot easier to work with, a lot more options as far as sealants and things like that go. And you can use them year-round. They work in all different types of temperatures. You don't have to worry about this formulation, that formulation. Drip edges, BIA will tell you, really, really important. I tend to agree. Whether you've got one with an adherent strip like this, or you're just putting a full bead of sealant all the way down that drip edge. But you want to be utilizing these. Here's one thing that's really changed. So with regard to installing flashing right into the bed joints of your CMU backup wall, really can't do that anymore, because if you picture, say, a 5-story building with flashings at every level installed, now your air barrier guy, whether it's you or somebody else, air barrier installer comes around. How is he going to maintain continuity of the air barrier around a pre-installed flashing? Doesn't really work. So what we're suggesting is, you know what, worry about the backup wall, worry about the prep work for the air barrier, get the air barrier on the wall, then 3 months later, when you're coming back with your brick anyway, install the flashing at that time, and just utilizing a termination bar to do that. And term bar, if you can use the term bar with the sealant on the back side of it and a bead of sealant across the top, again, I'm a belt and suspenders guy, so that works really, really well. Here's another item too. These were cost prohibitive when I started this game 15 years or so ago. These were coming out of my shop and they were really, really expensive. Now they're not. They're pre-stamped. They're mass produced. In reality, this is helpful to you because it makes for inside or outside corner installations of flashings a lot faster, a lot easier. If there are a few extra bucks, you're probably going to save that from the labor perspective of not having to go through that workmanship of forming a good corner or end dam. Finishing up here with weeps, again, as I said before, we want those weeps at the bottom of the wall and the vents at the top of the wall. Code used to be 36 inches on these. Now that code is actually 24 inches, and I'll tell you, a lot of specifiers that I work with are specifying them at 16, again, just to help equalize that pressure. Whatever you're using, though, make sure that they are installed to the prescriptive code, and make sure that they stay clean behind them is just absolutely key, so that we're not holding any moisture back in that wall. And again, it's not just about moisture; it's about air as well. Mortar collection devices, as you know, they'll suspend mortar at 2 different heights, allowing for proper drainage of any moisture that's in the wall, but also these are there for airflow as well, and that's really key that those are being utilized. So we're done there today. The only other thing that I'll talk about briefly is that you should be looking for sort of a single source on the supply end for as much of the stuff as you can get, because as you know, you scramble around calling me or anybody else for letters of compatibility between this material and this material, that material and this material. the more of the stuff that you get from that single source, okay, anchors to air barrier, flashings to air barrier, flashings, the drip edge, the less of that type of thing that you're going to have to go through with worrying about, is this mastic compatible with that drip edge? Is this primer compatible with that air barrier? You have to deal with that a lot less. And if you can sort of turn that around and look at a warranty on the wall as a system, rather than a warranty on your air barrier, a warranty on your flashing, a warranty on your anchorage, a warranty on the drip edge, or this or this or that, you're looking at basically creating a wall warranty and keeping it that simple, keeping the compatibility issues straight and simple. Really just, it makes it a lot easier for you, makes it a lot more clear to the owner that you're building the building for, just look for someone that can help you do that. So really that's my time. I appreciate everyone else's, and I see we're pretty close to the hour mark, but I can certainly hang on if anybody has any questions. I'd be more than happy to answer them now.
We do have a question. The question reads, which version of the TMS 402/ACI 530/ASCE5 code are you referring to? The TMS/ACI code 211 version has been adopted in many locations wherever the IBC 2012 was adopted, and there is also a 2013 TMS code recently written that supersedes ACI's involvement. When you say that ACI code is out of date or not current, which version are you referring to?
Well, it depends on where you are, because that certainly varies from state to state. I know states that are still working on 2008 version. There are some states that are working with 2011, it just depends certainly on where you are. I think the book that I have sitting on my shelf is from 2011, I would think, but I don't know that there's much difference from year to year.
Okay, we have a second question, and it says the 2011 version of the TMS code, the latest that is generally adopted, requires a drainage plane in front of the continuous rigid insulation in its cavity walls. How do you address the new code requirements for wall drainage planes in your wall sections?
Well, it depends on the size of the cavity. If we have cavities that are at an inch or less, then we like to see a continuous geotextile being put up so that we don't have any mortar bridging occurring from the brick to the face of the insulation. However, it's acceptable by BIA notes to anything that's an inch and a half or greater to just drain as it is.
Okay, let's see if there's any more questions. We have another question. Less than 1 inch cavities are no longer allowed?
They are not allowed. You're correct. However, there are sometimes circumstances with which they have to be utilized. So as an example, in reskinning a building in New York, where you're limited as to how much space you can actually utilize, anything that's existing, 1 inch cavity is actually quite common, as is, say, even a half an inch cavity in that case. So ideal, no. Allowed in new construction or necessary in new construction, no, but certainly those do occur.
Okay, and another question was, the BIA notes often refer to pre-TMS codes. I think that may have been a comment.
They can. I mean, BIA notes are written, and there's some BIA notes on there that are as recent as probably the last 3 or 4 months, and there's some notes on there that I know were written probably 15 or so years ago. So make sure you know what the note is that you're reading.